Hello everyone. On today's episode of Tinkering with Terrius, we're going to take a look at reed switches. Okay, so here is a reed switch, and the reed switch is made out of a little glass vial, and that glass vial is hermetically sealed. Inside the glass vial are two tabs, and then there are two leads coming out of the glass vial. So a reed switch is a magnetic switch. When a magnetic field is applied to the switch, it will either open or close. So this switch is a normally open switch, which means that when a magnetic field is applied to it, those two little tabs will close and make contact, allowing current to pass. You can also get normally closed reed switches, which do the opposite. When a magnetic field is applied, they will open and break the current. So the reason I want to play with this is because I plan on making a battery capacity meter out of a clock, a reed switch, a couple resistors, and a battery. In order to do that, we need to understand how the reed switch works. Okay, so we have the reed switch in a circuit here, and the circuit consists of a 1K resistor, a red LED, and a 3.3 volt power supply. As you can see, normally in this circuit, this reed switch is open and therefore there is no current flowing through it. If we take this hard drive magnet from a 2.5-inch hard drive and apply the magnetic field to the reed switch, you can see that the LED turns on. So we won't be able to trigger this reed switch with a magnet in our battery capacity meter, because what we want to happen is we want this reed switch to turn on and off the clock. So in order to make this reed switch turn on and off the clock, we need a magnetic field applied to the reed switch so that it turns on, and that magnetic field needs to be applied when the battery is connected that we are testing. Now we also need that magnetic field to turn off once the battery gets down to a low enough voltage. So the solution to this is going to be to make this little reed switch into a reed relay. Now that might sound complicated, but it's really not. All a reed relay is a reed switch with a coil wrapped around it. Then of course you apply the current to the coil, and that will generate a magnetic field. That magnetic field will then turn on the reed switch. So we have a couple coils here. There's this littler coil, which is basically just one layer of magnet wire around the reed switch. And then we have this larger one, which is kind of permanently attached to this reed switch, and that one is two coils around it. What we're going to do is we're going to take the benchtop power supply, we're going to set it at a fixed voltage, and we're going to see at what voltage and what amperage the LED will no longer light with these two coils. Now it's also important to note that when you're handling the reed switches, be very delicate with them. They are little glass vials that are very fragile. So of course, because of the nature of having steel or metal leads coming out of it, if you bend these in the wrong way, you will end up breaking the little glass vial. Now these end bits can break without any damage to the reed switch, but if you break off nearer to the middle, then the whole reed switch is going to fall apart. So ideally bend it back fairly far. On this side I bent it way too close to the reed switch and it broke off quite a large chunk of glass there. So it's fairly important to test your reed switches first before you actually try to use them, because in my package of 10, 3 of them did not work, and it appeared as though the heat treating that's supposed to happen to one side of the internal tab did not happen on those 3. That's a fairly good indicator. So the problem with this particular coil is that there are not enough windings here to produce a magnetic field that's strong enough to activate the reed switch. However, if we apply a second resistor to kind of have the resistance here and increase the amount of load, you'll find that we do actually get plenty of voltage. So with a 1.1 ohm load, we are okay. Now, of course, with a 1.1 ohm load, we are only drawing 0.9 volts at 600 milliamps. We're going to turn down the milliamps. There we're losing down to 0.7. Between 0.7 and 0.6, the LED stops lighting. And the interesting thing here is that it actually takes a stronger magnetic field to initiate the reed switch than it does to maintain the reed switch. 400 milliamps, the light stops. When we go back up to 500, it doesn't turn on. When we go to 600, it turns on. And when we go back down to 500, it doesn't turn off. When we go down to 400, it does turn off. We're going to put this at 0.8, quite a bit of amperage. And now we are going to dial back the voltage to see at what point does this cut off. So we're actually going to come here to the lowest value, and we are going to start dialing it back. And keep an eye on the LED to see when we hit the minimum voltage that this particular coil can handle with this load. Now, of course, at this load, it's going to deplete a battery relatively fast. There we go. Okay, let's go back up to get this to turn back on. Let's just pay attention. 0.28. There we go. So at 0.76 volts, this LED turns off. That is a fairly low voltage, and that should show the capacity of most of the battery, but it's still going to be drawing a substantial load and depleting that battery further without the clock actually registering that. So instead, what we are going to try is our beefier coil, and we're going to see if the more windings will allow this to run a little bit better. We are going to turn the amperage down just so we don't do anything terrible. We're going to turn off the power supply, disconnect the positive first, and let's test out our other reed switch. Let's turn it up and see at what point this turns on with the extra windings. And what point does it turn off? So it turns on at about 0.59 volts, and it turns off at 0.51 volts. For most AA batteries, I think that might actually be a good voltage and amperage to run it down to. On the other hand, we could add a second resistor here, which would allow us to go much further down. We'll turn on at about 3.3 volts, and it turns off at about 2.6. Either way, I believe what I'll have to do is set this up and then be relatively nearby so that I can see when the clock turns off. Hopefully it will be interesting to put this together. I'm not going to put it together today, but I will be putting it together soon. And if you're curious, the clock I'm going to be using is just this super cheap one from Amazon. It's got a standard quartz movement in there. We're going to have to jerry-rig it so that the battery here isn't actually there. I'll put a battery holder probably over here on the side, and then the other side there'll be the battery tester holder, and we'll run the wires and everything here. And it's probably just going to sit on a desk like that and slowly tick away the hours and the minutes. Now this video might not be terribly interesting, but if you were curious about reed switches, hopefully it helped somewhat. So if you liked this video, then be sure to give it a big thumbs up. If you have any friends that might be interested in this video, then be sure to share it, because shares and likes help a ton with the YouTube algorithm. If you have any questions, comments, ideas for future episodes, then be sure to leave them in the section below, or you can email them to me or tweet them to me. If you enjoyed this video and want to see more videos from me, then be sure to hit the subscribe icon, which should be around here, and don't forget to hit the little bell notification icon. Thank you for watching. I hope you have a wonderful day.